Mindsetters, welcome to today's Grade 12 Math Show. Today we have a special revision lesson on geometry. We have selected highlights from lessons shown earlier in the term to help you revise this term's work. So please post your comments and your questions on our Facebook page or on Twitter @LearnExtra so we can help you with your revision. You can also download the show notes for today's lesson from learn.mindset.co.za or click on the link on our Facebook page. Now it's time to get on with today's lesson.
Okay, so we've got question 1. Let's move it up to there. First things first, guys, when you are sitting with a Euclidean geometry rider like this, please take a moment to just read it very carefully. Okay, I would suggest have a highlighter in your hand, and just as you're reading this initial piece of information that they're giving you over there, highlight the important things, okay, because that will guide you as to which of the theorems that you're actually going to have to use, okay? So as an example, in the diagram, O is the center. Now that's really important information, because if we know that, remember we can use the first three theorems, okay? Of the circle HEATR. So that's stating that these 4 points or 5 points are sitting on the circumference of your circle, okay? AOF is parallel to EH. Okay, so that's important information over there. This line is parallel to that line. Now, that doesn't imply any of your circle theorems, but it most certainly implies your geometry that you learned in grade 8 and 9 with your corresponding, co-interior, and alternate angles. So remember, even though that's not circle theory geometry, you're still going to use it, okay? So remember that from earlier years. Okay, let's fill in what they've given us. Angle F2 is 78 degrees, we know that. And R1 is 22. Okay, calculate with reasons the size of the first one we're looking for is angle O1. So this is what we're looking for over here. Okay, so what can we see? O1 is an angle at the center of my circle. I think you guys all agree with me. I can see that over there. So what can we use? Could we use angle at center is 2 times angle at circumference? Well, unfortunately, no, because we don't know what H1 is yet. Okay, so if we knew what H1 is, great, but we don't, so we can't use that. Let's use the information that was obviously given to us. We know that, let's use a different color. We know that this is 78 and that's 22, and those are 2 angles inside this triangle over here. So do we remember the reason that states that if we've got an exterior angle of a triangle, it equals the sum of the opposite interior angles, okay? So therefore, if I've got 78 and 22, if we add those up, we should get to 100. So angle O1 is going to be equal to 100 degrees, and my reason for that is because of exterior angles, or just angle of triangle, okay? So we now know that that's 100 degrees. Right, next one, angle H1. Excuse me. Angle H1. Now, this is where I pointed out earlier that an angle at the center is going to be 2 times the angle at the circumference. So angle H1 is going to end up being half of angle O1, which is 50. And that's angle at center equals 2 times angle at circumference. Okay? Right, angle T. Let's see if we can see what angle T is. This is angle T over here. Okay, so angle T, where is it? It's sitting on the circumference of your circle, all right? So that would imply to me that we need to see if we've maybe got a cyclic quad here. And if we look over here, I'm going to try and use a different color. I don't want to make it so many colors that you can't see. But we've got 1, 2, 3, 4 different sides. So do we spot the cyclic quad over there? Okay. And if we know then that this angle over here was 50, we know that the opposite angles of a cyclic quad are supplementary, which means that this angle of angle T is going to have to be 130 degrees because opposite angles of cyclic quad. Okay. Right, and that finally leaves us with H2. Let's see where H2 is. This one over here. Now, let's not forget that we were given these parallel lines over here. So using that, remember, they're not going to tell you that if they don't want you to use it. Do we remember the theory that said that if we've got alternate angles between parallel lines, they're going to be equal to each other. So if I can work out what angle A2 is, then using your alternate angles, we can get to angle H1, okay? Now that would mean the challenge is we have to find A2. And I want you to look at this triangle over here, okay? We've got an exterior angle, which is 78. I've got an angle inside here, which we know is 50. And that leaves me with this angle A2 over there, which is what we're going to have to work out. So basically, the sum is this. We're going to have to take the exterior angle, which is 78 degrees. And that's going to work out being the one angle of 50 plus the other angle of angle A2. Okay, so obviously then 78 minus 50 is going to leave you with A2. 78 minus 50 is going to leave us with 28. So angle H2 is going to be 28 degrees, and that was because, oh wait, hang on, sorry, I haven't got to H2 yet. Sorry, angle A2. So we've actually got an extra step here. Angle A2 is 28 degrees. That was because of the exterior angle of triangle. So therefore, angle H2 is also going to be equal to 28 degrees. Reason is because of alternate angles. And please don't forget to state parallel lines. AF is parallel to EH. Right, there we go. All right, guys, let's have a look at another example. All right, so as I said to you in the previous example, have that highlighter out and just take very careful note of the information, the little clues that they're giving you when they give you that introduction paragraph. Okay, so the figure alongside RS and RNP are tangents. Okay, there's our first clue. So we've got tangents to the circle with the circle center O. So again, we've got the circle center, which allows us to kind of think about our theorems of angled centers 2 times angled circumference, possibly your midpoint chord theorem, your very first one, or we could be looking at possibly your diameter subtending a 90-degree angle. So just have those at the back of your mind. Just remember those are the ones that could come up here. Okay, radius. Okay, the radius NO, so the line from the center to the circumference is a radius, is produced and cuts the circle at M and meets RS produced at T. It's not that that's not important information. It's obviously just clarifying what exactly they've done there, but it's not going to imply or use any theorems as such. That's just helping you make a very clear understanding of what's happening in the diagram. Okay. All right. So the first thing they're asking of us is why is RSQ equal to 90 degrees? Okay. Well, let's identify. So angle RSQ. RSQ. Is this? It's probably O. Anyway. Okay. This one over here. This one over here. Why is that 90 degrees? What's the reason as to which that's 90 degrees? Well, I hope you've all identified this. I hope you've all identified that that's a radius and this is a tangent, both of which we were told in the write-up earlier, so we all know that that's the case. And we know that there's a theorem that says that a radius and a tangent are perpendicular. So why is RSO, or sorry, I think that is supposed to be RSO, is it equal to 90 degrees? Why? Because a radius is perpendicular to a tangent. Okay. Right, then they go on to say, prove, all right, that RNOS is a cyclic quad. Let's just highlight that quickly. RNOS. So there's our quadrilateral, our 4-sided figure. And they're basically saying that if there was a circle drawn around those 4 points, we have to prove that those four points would be on the circumference of the circle, okay? Now, what's important here, guys, is we need to think about how would I go about proving it's a cyclic quad, okay? You can either prove that the opposite angles of that quadrilateral are supplementary. So we can prove that the 2 opposite angles add up to 180. That's one way of proving it. We could prove that the exterior, if there's any line that's been extended on your quadrilateral, we can prove that the exterior angle equals your opposite interior angle. That's another way of proving it. Or we can prove it by means of proving angles in the same segments. Okay, I always use the shortcut of calling it the bow tie theorem, and I'm sure you guys possibly have heard that as well. So proving that you've got that bow tie shape inside of where your 4 points are touching the circumference That's another way of proving a cyclic quad. So those are your 3 ways in which you want to try and do this, okay? So let's see. I know that I've got a 90-degree angle over there, and believe me, they haven't asked you to prove that unless they wanted you to use it. The other thing to watch out for is that we have another radius of ON, and we've got another tangent at RP. So wouldn't we have the same situation that a radius and a tangent would be perpendicular to each other? Okay? So therefore, let's just write it over here. So here we're solving question B. So the first statement we're going to make is that angle N1 plus angle N2, those angles together, are equal to 90 degrees. Why? Because we've got a radius perpendicular to tangent. Okay? And if I've got a 90 degrees over there and a 90 degrees over there, then do you guys agree that the opposite angles of that quadrilateral are adding up to 180 degrees? So without any other working out, we've actually proven that it's a cyclic quad. So we can make the statement, we can say, therefore, our RNOS is cyclic. And why? Because the opposite angles of the quadrilateral, okay, we can't call it a cyclic quad, because remember, that's what we're proving it is, okay? So it's just the opposite angles of the quadrilateral are supplementary. And that's your converse theorem to the opposite angles being that they add up to 90 degrees. And that's it. There we go. So now we've proven that it's a cyclic quad. Okay? That done, let's see what the next thing they're asking of us is. If angle S is equal to x, determine with reasons 4 other angles in the figure which are equal to x. Okay, so let's see. Let's use blue over here. Angle S is equal to x. Okay. If I'm not mistaken, guys, there needs to be a 1 over there. Let's just correct that. So we've got our x over here, angle x, S1. All right? That angle over there being x, we need to prove which other angles are equal to x. Well, the first thing I want to draw your attention to is the fact that we've got a tangent and we've got a chord. Okay? And if we run our fingers along that chord all the way down to where it touches the circumference, we get to this point over here. Okay, and that was angle N. I think I'm going to have to erase all my writing there so we can see what angle it actually is, angle N2. Okay, let's put back to blue. So it was angle N2. So that one over there is going to be x. So this is question C. So first things first, we're going to say that angle N2 is equal to x, and our reason for that is tan chord. Okay. Right, if that's equal to x, the next one's going to be quite interesting. We've just proven that we've got a cyclic quad with RNOS, okay? And if we've got a cyclic quad, it means that all 4 points are touching your circumference. So therefore, as a result, do you guys see that I've got a bow tie? Okay, so I've actually got an angles in the same segment, which would mean that R1, so angle R1 is also equal to x because of angles in the same segment. Oh, okay. Hope you can read that. All right. Now that we've got that, what else can we use? We have got. Okay. Here's something interesting. We have radiuses. Okay, we've got a radii at least. Sorry. So we've got OS and we've got ON, and those are radii. So therefore, what type of triangle do you have there? Isosceles. Okay. And equal angles, so remember that's an x over there, equal angles are opposite equal sides. So the next statement, I'm going to have to write it on the other side here if you don't mind, is going to be S3 is also equal to x because of angles in the same segment. No, it's not angles in the same segment. It is an isosceles triangle, which is equal angles opposite equal sides. And finally, if that's x over there, I hope you guys are following all the colors, there's another bow tie. Okay, do you see the purple bow tie there? Which means that that's x down there. So finally, angle R2 is also going to be equal to x because of angles in the same segment. So something I'd like to point out to you. can you guys see that having proven the cyclic quad was really, really helpful in the following question where we had to find various angles equal to x. Okay, so please remember that when you're solving a rider, whatever you solved in question A followed by question B is probably going to be used as you follow through into question C and D as to help you actually solve the rest of the sum. So once you've proven it, you can use it as part of your solving. Okay. And finally, prove that angle S3 is half of angle O3. Okay. Let's try and clean this up a little bit so we can actually see what's going on here. Otherwise, it becomes a bit messy. Okay, so angle S3. Okay, so there we go. It looks a bit better. And the other thing I'm going to quickly do is I'm going to just put back. So we said that this one was X. We said that this one was X, we said that that was X, and we said that that was X. Okay, so prove that angle S3 is half of O3. So S3 is this one over here. We're trying to prove that it's half of O3. Well, the first thing I know is this. Do we all see that O3 is being subtended by that chord SM? And it's being subtended at the center, all right? Now, the same angle that's being subtended by your chord of SM is this one all the way over here at angle N2. Now, we know that angle N2 is X, which means that this angle of O3 is going to have to be 2X because angle at center is 2 times angle at circumference. Okay? But we already knew that angle N2 was equal to angle S3, and that we can say was proven above. All right, we had already proven that. So as a result, it can then be stated that angle O3 is twice the size of angle S3, which is what they were asking you to prove. Okay, so I haven't set that all out for me. I hope you've just followed what I've said, and you would need to set that out nicely as well. Okay.
Okay, guys, I hope you're enjoying this revision session. If you are struggling and need help, please post on the page or send your questions to the Learn Extra Help Desk. The links are on our Facebook page. But now it's time to take a very quick break. Don't go away. We'll be right back. Welcome back from the break, guys. Doing revision is really important, so I hope you are enjoying this lesson. I'd love to chat to you on our Facebook page or on Twitter, so please let us know how you are doing. Enough of the chat, now it's time to get back to some more revision.
Okay, so just like I've been saying with every other question, start by reading that initial piece of information very carefully, okay? In the figure below, A, B, C, D, and E are points on the circumference. Okay, that's important, guys, because that implies that we can use cyclic quads, okay? Point on the circumference with a center of O. Okay, remember your first 3 theorems with regards to that. TBS is a tangent, okay, very important, to the circle. DB and AC intersect at X, so they're just clarifying where those 2 lines intersect. And then we were given that angle A1 is 60 degrees, so we've got a 60 degrees over there, and C2 is 40 degrees over there. Okay, right, and they've asked us all the different types of angles, and we're having to find their size with reason. So let's see if we can have a look at the first one. Let's make that green. Right, angle C1, we're looking for this one over here. How are we going to be able to find that? Obviously, we have to now turn to the size of angles that we do have, which is 60 and 40. And what I'm going to point out to you here is that do we all agree that angle AO and, line AO and OB are both radii, okay? And radii we know are equal. So here's my first thing. Let's write, this is answer to A. The first thing I'm going to state is that OA is equal to OB. The reason for that is because they are radii. Okay, that would mean, okay, so there's a therefore there, that angle B2 and 3, so angle B2 and 3 together are also equal to 60 degrees. Why? Because equal angles are opposite equal sides. Okay, right, so we know that that's 60 over there. that would mean that angle O1, so another therefore, angle O1 is going to also be equal to 60 degrees because that's interior angles of a triangle. Okay, so we've got a 60 degrees over there, interior angles of a triangle. Okay, and the reason why I wanted to know O1 is because if I look at my chord AB, let's do it in a different color just so it's clearer. Chord AB is subtending angle O1 at the center as well as subtending angle C1 at the circumference. And we know the theorem that says that angle at the center is twice the angle at the circumference. So that means that angle C1 is equal to 30. Angle at center equals 2 times angle at circumference. Okay, right, so we know that that's 30. First one done. Okay, there's our 30. Right, angle B1. Where's B1? Okay, that's this one over here. Okay, angle B1 is the angle that's being sandwiched between the tangent and the chord. Okay, so here's my chord AB again. So we're back to chord AB. And if I were to run my fingers along chord AB all the way to the circumference, we get back to angle C1. Okay, so that means there's a tan chord theorem there between C1 and B1. So B1 is also equal to 30 degrees. And our reason, guys, I don't have space, so I'm not going to write it, but you do need to write it next to it, that the reason why it's 30 is tan chord theorem. Okay? All right. Then we've got D1. All right, let's find D1, which is over here. What's D1 going to be? Well, if we look at it carefully, we've got 4 points sitting on the circumference, and they make our nice bow tie. All right, so we've got angles in the same segment. If that's D1 over there, it's going to be equal to 60. So D1 equals 60 degrees. I've got space problems, but you don't, so please next to it right there, angles in the same segment. Okay, that's your reason for your bow tie. Okay. Then E1. Okay, E1, let's see, or angle E at least. Okay, we're looking for this angle over here. Okay, that's an angle sort of sitting there, hovering around on its own, but let's see if we can see a reason as to why. Okay, I can see a reason over there. So I'll use a blue. Let's try and make it a totally different color. Do you see the cyclic quadrilateral here? It's a little bit obscure, so you don't notice it straight away. But in blue there, do you all see the cyclic quad? Okay. Now the cyclic quad would mean that your opposite angles are supplementary. Have I got B2? Have I worked out B2? I've got B1, which was 30. Is that going to work for me? Let's just see. B2. Give me a seckie here, guys. Let's just see if we can figure that out. I'm not seeing that. We need to get this one over here. Okay, give me a minute and I'll come back to that. Yeah, okay, I'll come back to that in a minute. Let's have a look and see if we can find the others. B2, okay, that's a bit... Oh, there it is. Okay, sorry, I can see it. If that's 40, this over here is going to be 40 because they were angles in the same segment. Angles in the same segment as your bow tie, which meant that this one over here was 140 because they were opposite angles of a cyclic quad. So that was 140 opposite angles of a cyclic quad. Angle B2 was 40 degrees because of angles in the same segments. Okay, so I hope you guys can see that over there. And finally, angle X1. Okay, angle X1. Sorry, it all becomes a bit colorful. In fact, I know this is a little bit contradictory because I'm using a lot of colors here, but just be careful to use too many colors in these riders, because what happens is it's very difficult to start deciphering what you're doing. So use color, but just be careful that you're not overdoing it, because it can actually land up being counteractive and causing more of a problem. All right, X1. So it's this one over here. Okay. We know that we've got a 60 degrees here, and we've got a 40 degrees here, and we've got this little triangle. Okay. So 60 and 40 we know is 100. That means that X3 is going to have to be 80 because of interior angles of a triangle. We have to state that. Okay, so please make sure that you state, first things first, that angle x3 is 80 because of your interior angles of triangle. And that would mean that angle x1, if we take a look at it, this is something we haven't used yet, they're vertically opposite. Okay, x1 and x3 are vertically opposite each other. So x1 is also equal to 80 degrees because of vertically opposite angles. All right. Queen, did anyone give us all the right answers there?
I think we do have someone who did give us all the right answers.
Oh, brilliant.
And Londang Ngema
Fantastic.
and Mahlabani Listufi Floyd also gave us all the correct answers.
Well done, guys.
Well done to you guys. Big ups.
Absolutely, well done. So practice, practice. The more you practice, the easier these get. Okay, so well done to you guys. That's fantastic. Right, we do have time to do one more example, so I'm going to make you do the practice again, and let's do a little bit more, okay? All right, very quickly, we're going to refer to the diagram. O is the center of the circle. So I hope you guys are getting the idea about taking note of these things. The diameter KL is produced to meet NM, which is produced at P. The diameter, guys, if they're telling you've got a diameter, look for it subtending an angle of 90 degrees. I would say almost 99% of the time, you're going to use that, okay? We've been told that we've got parallel lines again, so there's my parallel lines. And we know that angle F is 76 degrees, so that's given to us over there. First things first, we're going to calculate the size of angle L1. So looking at it carefully, point F, point K, point M, and point L are all sitting on your circumference. So do we see the bow tie that we've got over there? All right. So angle L is going to be equal to 76 degrees because of angles in the same segment. Angles in the same segment. Okay. Angle O1, well, if we've got angle, let's see, we've got O1 over here. Angle at center, 2 times angle at circumference. Do we have anything with that? Let's just see. No. All right, let's see what else we can use here. Angle at center, 2 times angle at circumference. Am I missing? Let's see, do we have tangents? No. Parallel lines. Okay, so let's look at this. Parallel lines. Okay, so we know that this line over here is parallel to this line over here. Do you remember that we've got a reason that's co-interior? Okay, so 180 minus 76. 180 minus 70 is 110, minus 6 would be 104. So this angle over here is going to be 104 degrees because of co-interior angles. All right? Guys, to save time, I'm not going to write this all down. I just want you to follow me so that we can get through all of it. So that's 104 degrees. And in fact, that's going to be 76 degrees. Either because you're doing adjacent angles on a straight line, or in fact, if you can spot it, we've got a corresponding angles over here. There's an F shape over there, all right? So you've got corresponding angles where ON is parallel to NLM. So that's why O1 is 76 degrees, okay? The next one, I'm just going to fill that in over there. Angle M4. M4 is this guy over here. What have we got in terms of its angle? Do we have angles in the same segment? Parallel lines. Let's see what we've got. Angle at, okay, this is quite a nice one over here. Your chord KN is subtending O1. And can you see that it is also subtending M4? So M4 is half of 76. Half of 70 is 35, 38. So M4 is 38 degrees because angle at center was 2 times angle at circumference. Angle N1 and 2, okay, what have we got for angle N1 and 2 over here? We have got a 90 degrees. That's your, okay, this chord is subtending an angle of 90 degrees. So there's a 90 degree angle over there. Is that going to help me? No, there's your cyclic quad. F, K, N, M. Okay, cyclic quad. And N1 and 2 is opposite 76. So that's also going to be 104. So N1 and 2 is also 104. because of opposite angles of a cyclic quad are supplementary. Angle M1, okay, this one over here, let's use a quick different color. Angle M1 is going to be, let's see, we've got parallel lines. We've got a 90 degrees over here because that's co-interior. We've got a cyclic quad. Sorry, I'm running out of time a little bit, so we might not finish this all. We've got a cyclic quad, so M1 is the exterior angle over there. So if we know K1 and 2, I can't remember if we've had to work that out. You'd have to find K1 and 2, and then once you've got that, you'd be able to find angle M1. And finally, the last one is that you had to prove that KG was equal to GM. The reason I wanted you guys to see this one was because we actually have got this. You've got an angle at the center. You had a 90 degrees over there. This is 90 degrees because you've got co-interior angles with the parallel lines. Now, the reason why that works is because the line from the center is perpendicular to the chord, which means that the chord is being cut in half, which was all the way back to Theorem 1. So go back and have a look at that and just work through that carefully, but at least you have all the answers to that.
Okay, guys, I hope you're enjoying this revision session. If you are struggling and need help, please post on the page or send your questions to the Learn Extra Help Desk. The links are on our Facebook page. But now it's time to take a very quick break. Don't go away. We'll be right back. Welcome back from the break, guys. Doing revision is really important, so I hope you are enjoying this lesson. I'd love to chat to you on our Facebook page or on Twitter, so please let us know how you are doing. Enough of the chat, now it's time to get back to some more revision.
The point of these guys is the more you do, the more familiar you're going to become with those theorems, and it's really going to become second nature to start looking for those little things that do come up more often than you think they do. So these are not a complete mystery. The more you do of them, the better they do get. Right, let's take out our highlighters and let's make sure we are identifying the important information over here. Tangent, there's the first important word. Tangent BC touches the circle ABDE at B. So obviously making it clear that all of those points are sitting on your circumference. Chord AD and BE intersect at F. Okay, so that's just giving you a bit of detail there that you can see that the lines cross each other at point F. And chord ED is produced. Produced means it's carried on in a straight line. Okay, so it hasn't changed angle. It's just continued in a straight line to C. And here's an important piece of information. AB is parallel to ED. So these guys are parallel over here. And obviously, again, guys, that implies corresponding co-interior or alternate angles. So just be aware of that. We're definitely going to use that somewhere along the line. What have they told us? They've told us that B1 is an angle of X degrees, and A1, they've told me, is Y. All right? And what they're asking me to do is to determine the magnitude, okay, another word for the size of angle C in terms of X and Y. So understand you're not going to get an actual number or an actual size for angle C. What you're going to do is land up with an answer with an X and a Y in your answer. Okay. All right. So with that in mind, let's see what we can do. The first thing I can see over here is that I've got an alternate angle. Okay, that jumps out at me, and I can see that these lines are parallel, so we've got alternate angles over there. So I can see that that angle over there is X. Okay, so let's fill that in. Angle E is equal to X because of alternate angles where AB was parallel to ED. Okay, the next thing that jumps out at me is my bow tie. All right, and do you guys see the bow tie here? All right, so that's your angles in the same segment, which means that this angle of X is going to be that angle over there. It's also going to be X. Let's make them green so we can see nicely. Okay, so angle D, let's call it, let's be specific, FDE, in fact, is the actual size of it. If we're specific, then there's no confusion when you're writing an exam. So FDE is also equal to x, and our reason for that is angles in the same segment. Okay, right, what else do we have over here? We do have an angle of y, so let's not ignore that for now. No, in fact, sorry, I can see one more x over here. Using my bow tie again, can we see the other side of it? That if this is x, then this would also be x, because we've got our angles in the same segment on the other side. So angle A2 is also going to be equal to x, also because of angles in the same segment. Okay, right. Okay, now we haven't used the y yet, so let's see if we can somehow find a place to fit that into the whole thing. We haven't used this yet, okay? So a good suggestion, guys, is that if you're doing a rider and you get a bit stuck, you can't quite see where to go next, go back to what they've told you over here, because often you get reminded, oh yeah, they told me I have a tangent and I haven't used that yet, okay? Which I do have a tangent over here, and tangent between the angle and the chord equals the angle in the opposite segment, so therefore that equals x plus y together. So this angle over here is an x plus y. Okay, so let's write that down. So angle B2 is equal to x plus y tan chord. Tan chord, okay? Now, let's see, we're trying to get to C. Don't forget, that's what we're actually trying to head towards over here. So at this point, do we spot this? We've got a triangle. Okay, there's a triangle over there. And I happen to already know that angle of the triangle, and I happen to know that angle of the triangle. So to find angle C is actually quite simple, because we know that the three angles in a triangle add up to 180 degrees. So finally, to find angle C, we're going to say 180 degrees minus the x plus y at B2 plus the angle x at angle E. And we can simplify that, which is going to be 180 minus, that's going to be a 2x minus y. Okay, and we can't simplify that any further, so we'd have to leave it like that. So find C in terms of x and y. There we go. That's for angle C in terms of x and y. And we haven't given it a reason yet. Remember, it's angles in a triangle. We should actually say interior angles in a triangle, because that's then clarifying exactly which angles we're talking about. So it's the interior angles of a triangle. All right, so again, go back, make sure you're really reading what they're telling you over there. And if you're getting a bit lost, go back to what they've told you. And remember, just maybe they gave you a clue in there which you haven't taken note of, and it's actually there to help you. Okay. Following on from this question, it then goes on to say, we've got John and Becky, and they're having a little argument here. John says to Becky, I'm sure I can prove that quadrilateral BCDF is cyclic. And then Becky says this is impossible. So what we need to establish is who's correct. Okay, who's the one that's right here? BC, where is it? BCDF, okay. That's this one here, BCDF. So we're looking at this quadrilateral. John says it can be a cyclic quad, and Becky says it can't be a cyclic quad. Who do we agree with? Okay. Well, again, what are the three ways of proving cyclic quad? Opposite angle supplementary, exterior angle equals opposite interior angle, or angles in the same segment. Because we don't have any diagonals here, we can toss angles in the same segment away. We're not going to use that. So let's look at possibly an exterior angle. Do you see that this angle x over here is the exterior angle of the potential cyclic quad? Okay. But if it was cyclic, that angle x would have to equal that angle B2 over there, which we can already see doesn't. It doesn't work, because if that's just x and that's x plus y, it's most definitely not the same. So who is correct? Becky is most definitely correct that it's not a cyclic quad. And why? Because the exterior angle is not equal to a positive interior angle. let's read it carefully. In the diagram below, the chord XY is produced by its own length 2a. All right, there, guys, the value of that statement is that it's saying that your line from x to y to a is all a straight line, so there's no curve or bend in that line. And tangent, okay, so tangent AZ is drawn to touch the circle at Z, okay, so there's our point over there. And XZ is produced to meet the line perpendicular to XA at B. So there's the 90 degrees that they're referring to over there. And AZ, the line AZ is equal to AB. So this line over here is equal to that line over there. All right, so they've given me a bit of information there. Let's see if we can start by finding the first thing. I'll leave it like that. Question 1. Prove that Z3, the angle of Z3, is 90 degrees. So this is my angle of Z3 over here, and I have to prove that it's equal to 90 degrees. Okay. Right, what I'm going to suggest is this. There's no numbers here whatsoever. They haven't given me any angles or sizes of angles. So a good starting point is you need to try and call something x, okay, because it just gives you a value to work with, and you'll find that it actually is very useful, okay. Now, no one's guiding us. No one's telling us where to call anything x. So this is a little bit up to you. You have to figure this one out yourself. But they're helping us a little bit over here because they have told me that I've got AZ and AB equal to each other. So I hope you're remembering that if those two lines were equal to each other, then these two angles would be equal to each other. Okay, so I think that's quite a good place to put our x, because both of those angles would then be equal to x. Okay, so the first statement we're going to make is the following. We're going to say let angle Z1 equal x. Okay, please make note that if you do call something x of yourself, you need to tell your teacher what it is that you're starting with. So please make that statement. Let whatever it is equal x. Therefore, we're going to be able to say that angle B is also equal to x. Okay, and our reason for that is because we have equal angles opposite equal sides. Equal angles opposite equal sides. Okay. Right, what else can I see? I'm trying to get Z3 to equal 90 degrees. Let's see. So I've got that as x over there, that's x over there. All right, I wonder if you guys can see this. I've got a very big triangle here. Big right angle triangle all the way from x to a to b. All right. So if I know that that's 90 and I know that that's x, then do you guys agree that we can work out this angle here because of interior angles of a triangle? So all three angles together would be 180. That's already 90. So 180 minus 90 is 90. And that's already x. So leaving us over here with a 90 minus x. Okay? So angle x is going to be equal to 90 minus x. And that's because they are interior angles of a triangle. And you can actually state it's triangle XAB, of triangle XAB. Okay. Right, now let's see what we've got over here. We have got a tangent. Let's not forget about our tangent. Let's highlight our tangent nicely. They told me that this over here is the tangent, that pink line over there. So let's look at this. If I've got a tangent, do you remember our tan chord theorem? The angle between the tangent and the chord equals the angle in the opposite segment. Yes. All right? So that means that you agree with me that angle Z2 is what?
90 minus x.
90 minus x, okay. So Z2 is going to be 90 minus x. And our reason for that, tan chord. Okay. Which is going to, okay, so I'm sitting with a 90 minus x over here. Are you seeing how we can get Z3?
Yes.
How are we going to get that?
Because we know that, isn't we have a tangent there? And then xz, no, they didn't tell us that they meet at at 90 degrees, so.
Okay, let me point this out to you. What about this? Have a look here. What do those three angles add up to together?
180 degrees.
180. Okay, now we already know that that's x, and we already know that that's 90 minus x. So if I take 180 and I subtract 90 minus x plus x, if we do the sum, what we should land up with is
90 degrees.
Okay, so there we go. So we can say then that angle Z3 is going to be equal to 90 degrees because of adjacent angles on a straight line. Okay, sometimes, guys, it's the obvious things you've got to look out for, so you always got to, and that just comes with practice, okay? All right, so now that we've done that, we've proven that this is 90 degrees, so let's actually fill that in so we remember if they've asked you to prove it, you've got to use it once you've proven it, okay? Okay, now they're saying prove triangle AXZ. So AXZ, which I'm going to have to just highlight as such, is similar to AZY. Let's highlight it in purple. AZY, that's this one over here. Okay, I hope that's clear to everybody. All right, guys, so the way we set out a similarity proof is we have to set it out properly. So I'm just going to scroll up for a minute, and we start off by saying, in triangle AXZ and triangle AZY, okay? In those two triangles, remember, guys, the challenge here is we have to prove similarity, we're either looking for an angle, or we're looking for sides in proportion. Now, obviously, I don't have any lengths of the sides of these triangles, so I'm not going to be looking at that condition. I definitely am looking for angle. And the really nice thing about proving three angles in a triangle equal is that if you manage to prove two of them equal, the third one has to be equal, because if the three angles in a triangle add up to 180 and two of them are already equal, the third will automatically be equal. So in fact, your job is cut down by a third. You only need to actually find two of them equal to each other. Okay, so let's have a look. We're trying to prove this green striped triangle equal to the purple striped triangle. And let's see what we've got. I've got an angle of, I've got a common angle of A over there. All right, what else do we have equal?
Z2 and X.
Z2. Okay, so we've got Z2, this one over here, and this one over here.
Yeah, equal also.
So there we go. That's all we had to use. Hey, so it's quite nice. Hey. All right. So angle A. So we start by saying angle A is equal to angle A in each of the triangles, and my reason for that was common. Okay, common angle. We can say that angle Z2 was equal to angle X. And what we can say there, guys, is that it's proven. We actually already showed that in the previous question, so we can just state that, okay? Leaving us with the last angle in each of the triangles. In the small purple triangle, this angle of Y is the third angle in the triangle. And in the big green triangle, this whole angle of Z is your big angle. So angle Y is equal to angle Z. And our reason there is it is the third angle in the triangle. Okay. Once we've got that, here's now a really important part of this. We can then say that, therefore, triangle AXZ is similar to triangle, but, okay, what do we have to remember over here? We've got triangle AXZ, and now I need to state the other triangle over here.
Yeah, you need to put them the way they were corresponding.
Exactly.
The angles must correspond.
Such a star. You've got to get it the right. You've got to get it in the right order. Okay, so let's just make sure we've got AXZ and AZY. Let's just make sure that that's correct. Angle A was equal to angle A. Angle X was equal to angle Z, and angle Z was equal to angle Y. So yes, we've got that in the correct order. And please don't forget to write that it's angle. Okay. Right, here's my favorite part of these. This looks so tricky. Okay, we've now got to prove that AZ squared is equal to AY times XA. It's so easy.
Yes.
All right, this is what we're going to do. This is what I call my eyebrows and my smile, okay? Because what I'm going to do is I'm going to do a little green eyebrow above the first two values in your first triangle, and I'm going to correspond it with another green little eyebrow over there. Then I'm going to have another eyebrow over the corresponding eyebrow there. And we're going to put a big smile between these two over here. Okay, and that's how you're going to set this up, because remember guys, if you've proven that the triangles are similar, you have proven that the sides are corresponding, they're in proportion. So therefore, here's our statement. AX over AZ is equal to XZ over ZY, which is equal to AZ over AY. And let's see, we're looking for an AZ squared. So what I want you to do is this. Look for AZ. I've got an AZ there, give it a tick. And I've got an AZ over there, give it a tick. And AY and X. So AY and XA, look there, they're all together. So what we do is we cross multiply. So AX times AY. And AZ times AZ is AZ squared, and we did that by means of cross multiplication.
We've come to the end of today's show. Thanks for joining me and for chatting to me during the show. Please visit our website, learn.mindset.co.za, to get the notes and to watch the videos from earlier in the year. And remember, we are here to get you through the year, so stay connected. Goodbye.